तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will continue with our discussion on the numerical methods to solve differential equation, ordinary differential equation as initial value problems, that is with all the boundary conditions specified at the beginning. So we were looking at the method called Runge-Kutta method in the last class. So in which the function which we have to solve, in the differential equation which we have to solve of the form y primed is equal to f of x y was split into two steps. In the case of a second order Runge-Kutta method, that is what we were looked at in the last time. Okay, so there is so let's just summarize that. So we have been writing the differential equations of this form, first order differential equations of this form f of x comma y. So this prime means the first derivative with respect to x, and this is a function of x and y. So then we said that we looked at various different methods of solving such differential equations with all the boundary conditions specified at the beginning. That is, this first order differential equation, there is only one boundary condition that is specified at x equal to x0, that is at the beginning, as y0. So that's an initial value problem. That's what we were solving, and we looked at some simple methods of solving this, including the Runge-Kutta method. So in the second order Runge-Kutta method, we write the solution as of yn plus 1 equal to yn plus ak1 plus bk2. Remember here, what we mean by solving such a differential equation is to actually find out what is the functional dependence of y on x is. Okay, so y at x for a whole given interval x greater than or equal to x0 to less than or equal to x1. So that's what we wanted to solve. So now to solve this numerically, we of course discretize this interval into n n points, and then write y of xn. Okay, now we'll denote this by yn, because that's a notation which we use. So y prime means the derivative with respect to x, and yxn is yn. So then we wrote yn plus 1, that is xn plus the next interval from xn, the next position after xn, that is xn plus h, can be written as, we said, yn plus a k1 plus b k2, and we said k1 is the function at xn comma yn, and k2 is the function at xn plus alpha h, and yn plus beta k1. Okay, so that was the method. That's the second order Runge-Kutta method, in which we actually wrote this as in this form, that is yn plus 1, that is given yn, given the y value at n, that is at any point xn. What is the y value at xn plus 1, that is the next interval xn plus h, that is h is the distance between xn plus 1 and xn. So what is the y value there, and that is given by yn plus ak1 plus bk2, where a and b are some coefficient which has to be determined, and k1 is the function value at x and y n, and k2 is this function value on the right hand side, the derivative at xn plus alpha h and yn plus beta k1, where alpha and beta are yet to be determined. Then the technique we used was to expand this. We could do two things. We could say that y at yn plus 1, that is y at xn plus h. I can expand it around xn using a Taylor series expansion and say that this is equal to y at xn, that is yn, right, plus the derivative of the function y primed, okay, at xn into h, right. So I could write this in this form, and then say the next one would be y double prime of x at xn into h squared by 2, etc. Okay, so I could expand this in this Taylor series. So that is, then I would get order h. So remember, h is xn plus 1. Okay, that h is the interval here. That is xn plus 1 minus xn. Okay, so we could get orders, this order h and order h square and order 0 terms in this expansion, and then we could do we could obtain the same thing by another way, that we could take this expression, okay, and then again expand the right hand side in a Taylor series. Okay, so when I do that, I can write, now this we got, so let me call this as 1, okay, and then we could start from here, that is yn plus 1 as yn, which is yxn, plus a times f of xn comma yn, right, plus b times k, so b times k2. Now k2 is f at xn, so f at xn plus alpha h, comma yn plus beta f at xn yn. We will call this as fn now. Okay. So now what we could do is, just like we expanded this on the right hand side, the right hand side of this equation, we could also expand this function here, okay, and do a Taylor series expansion of that. Okay. So that would lead to yn plus af, we call it af is f at x and yn, let me call it fn. So let me call that as sf, okay, because we have to write the derivative. So when I say f, it is just the value of f at x and yn, and then you could write b times, I could expand this around that, that is f plus the derivative of f with respect to x, which is fx I call, that is derivative of f with respect to x into alpha h. So similar as this, so derivative of f with respect to x times alpha h, and then derivative of f with respect to y and derivative of y. So I will write derivative of f with respect to y as del f by del y into del y by del h, okay, del y by del x. So that is 2 terms I get. So I will write as this as f times, sorry, I'll just write this here. F times fy, sorry, f times fx, okay, so fy I am writing, so I am writing fy as del f by del y into del y by del x, that is what I am writing there. So that is fy plus, so that is into beta k1, okay, so that is what I am expanding here. So this as k1 is f, so I just write it as beta f. Okay, so I could write this terms all in expansion like that. Okay, so all these terms. Okay, so then I could compare the terms of order from this equation to this equation. Okay, and then get the coefficients beta, b, alpha, and so I will compare all the order alpha terms and order h terms and order h square terms between this equation 2 and equation 1. And then I would determine a and b. Okay, so that's what the method was. So let me just summarize that once again here in this slide. So that's, I will write yn plus 1 as yn plus ak1 plus bk2, and then where k1 is hf xn yn, and k2 is h into f at xn plus alpha h and yn plus beta k1. And then I would just expand this term, right, y at xn plus 1 using a Taylor series expansion. So that is y at xn plus h times f, which is a derivative, and h square times the second derivative, etc. And then I would go back and there, and I would expand the term, I would go ahead and expand the next equation. That is, I would write this, I will expand this right hand side of this equation, which is what I just written on the board. Okay. And then I will write it as alpha h fx and beta k1 fy plus alpha square h square by 2 fxx, etc. So now we get these two equations by solving, by comparing 1 and 2, and then we would write a equal to b equal to half and alpha equal to beta equal to 1 as the solution of this equation. Okay, that's not the only solution, of course, because there are 4 unknowns, a, b, and alpha and beta, but this is one of the solutions. So we make a choice here. We have freedom to make a choice. So we will make a choice, and we say a equal to b equal to half and alpha equal to beta equal to 1 would satisfy these equations. Okay, so that's what we have done in the last class. And just summarize that here. So basically, I take this expansion, this equation, which is our solution, and expand the right hand side and the left hand side and the right hand side independently. That is, yn plus 1 is y at x plus h, which I can Taylor series, expand using a Taylor series, and I can also expand the beta k2 because k2 is this term, which also I can expand around x and yn. Okay. And then compare the two expansions, so the order h square and h terms, okay, and then I would get this terms that y, I would get an expression which that a plus b equal to 1 and beta alpha plus b beta equal to 1. Okay, so that's what I would get. So these two expressions can, from these two expressions I can solve. So I get that these two expressions I can solve and get the solution that a equal to b equal to half and alpha equal to beta equal to 1. So that's a summary which we did, and that would lead to an equation of the following form. So we would get the solution as, if I use a equal to b equal to half and alpha equal to beta equal to 1 as my solutions, as we have just written here. Okay. And then I can write yn plus 1 as yn, remember, plus a is half, so it's half times k1 plus half times k2, which is yn plus half times f at xn yn plus half times f at k2 was f at xn plus alpha h, alpha is 1, so xn plus h yn plus beta is again 1, so yn plus k1, so k1 is h times, so k1 is h times f, so it is h times f. Okay, that's what we obtained. Okay, so I forgot to write an h here, so there is actually an h term in all these equations. Okay, so because we were writing that, remember, we write k1 as h times f of xn comma yn, and k2 as h times f of xn plus alpha h plus yn plus beta k1. So there is an h in these terms here. Okay, so I write all that here. So this will become h by 2, and this becomes h by 2. Okay, so that's the equation. Okay, so that's what our yn plus 1 would be. Okay, so that's yn plus 1. So we can write it in terms of this, which is basically saying that it is yn plus half times hf derivative evaluated at xn plus yn, and derivative evaluated at xn plus h and yn plus hf. So now remember that this is nothing but our old predictor corrector method which we had looked at. So we said that there are two ways of the first method which you looked at. A simple extension of the Euler method. That is, in the Euler method we said that if you want to go to the next term, next position on the curve, then we use the function value at the given position and then multiply it by the derivative of that function. Add to that the product of the derivative and the interval. That was the Euler method. That is, in the Euler method we choose to write y in the Euler method. So we had Euler, we wrote yn plus 1 as yn plus h times f of xn comma yn, right. And in the predictor corrector method, which is a simple extension of this, we said I can evaluate it in two steps. Okay, that is, one is this, and then I would say that I would evaluate. So this I call as yn0. So in the predictor corrector method, we wrote it as yn plus 1 0 as yn plus h times f of xn comma yn, and then we wrote yn plus 1 as yn plus h by 2 into f at x and yn plus f evaluated at xn plus h comma yn plus 1 0. In that method we had a predicted value for yn plus 1 using the derivative at x and yn, and then we corrected that by taking a mean of this two derivative, that is, derivative evaluated at x and yn and the derivative evaluated at xn plus h and yn 0, that is a predicted value. And then we said that if these two didn't compare, that is, this yn 0 plus 1 0 and yn plus 1 did not compare, then we will go back and then do this again. Okay, that was the predictor corrected method iteration. So here we are doing exactly the same. We are just saying that in the second order Runge-Kutta, we are saying exactly the same. We are saying what we did by making this choice a plus b equal to half and alpha plus beta, alpha equal to beta equal to 1, is to go back to the predictor corrector and write it as yn plus h by 2 into f at x and yn plus f at xn plus h yn plus hf by 2. So that was our simple scheme of second order Runge-Kutta scheme. So we could just look at an implementation of this. Here is a code which does that. Okay, so this code would do a simple implementation of the second order Runge-Kutta scheme. So I have, again this code, just like our numerical integration scheme. Okay, here again we have x and y as discretized at endpoints. So I have given some upper limits as 2 and 0. So this is integral from 0 to 2 of a function. So we will see what the differential equation is. So take some differential equation, and then we have first order differential equation, and we have we have to solve this differential equation between two limits, that is 0 and 2. Okay, that is our x1 and x0. Okay, and I will have endpoints. I will choose endpoints in between. Okay, we will see how we choose the endpoints, etc. Okay. And then I have two arrays here, x and y. This is some pointers. Okay, in which I would put the values at which I am going to evaluate the function, and that is the independent variable and the dependent variable y. It's a first order equation, so we have only y of x is the solution of the equation. So then I have given here some memory to that variables, the pointers x and y, okay, by using malloc function. Okay, so and then I will print out the upper limit and the lower limit at which we are going to solve the equation, and that is this point. And then we would say this program would ask the number of points which you would like to have in between these two intervals. okay, and that is read off from the screen as n points, okay, which is given to n here. So our n would be the number of points at which we would evaluate, we would use, that's the number of points we would use to solve the equation. Okay, so then we had we will call this program called Runge-Kutta 2. So this is second order Runge-Kutta. So I just, to denote that, I put the function name as Runge-Kutta 2. And to this function we will supply the number of points at which we would like to use, the upper limit, the lower limit, and a pointer to a function called my function, because I need to tell the program which function, what is my right hand side. Okay, so because I'm going to solve an equation of the form, I'm going to solve an equation of the form y prime equal to f of x comma y. Right? So I need to tell the program what this function is. Okay, so that is so I would write a program separately for that, so a function for that, and I say I am supplying to this program, that is Runge-Kutta second order, that pointer to that function. And remember, when you supply pointer to a function like that, we need to declare it outside the main program. So that's what I have done here. So that function is declared here as my function, and it takes 3 variables, and that's all the 3 are pointers in this case. Okay, so 3 pointers into that function. Okay, so then we call that, and this we call a pointer, pass a pointer to that function, and then the x and y values. Okay, so now this program should return to us the x and the y. That is the function value evaluated at x. That is what this program would return. Okay, given the number of points which you would like to use, the upper limit, the lower limit, and a pointer to the function which would give the right hand side of my differential equation, y prime equal to f of x y. Okay. So then I would just print out this into a solution here. So a file called Runge-2 underscore solution dot dat. So that's what it will print out. Okay, so now what does this program do? This Runge underscore Kutta underscore 2. So that program just simply does a second order differential equation. That is it just solves. It writes the solution as y. So it writes a solution as yn as y of I plus the interval times dy dx, and then y of I plus 1 as y of I plus the interval times dy dx, that is the derivative evaluated at xn yn, and the derivative evaluated at xn plus h and yn plus beta yn plus f into h. Okay, so that's what we will see here. So first, so this program when we call, that is this program Runge underscore Kutta, which we call this program, and then that will again, the structure of this program is the following. So that you are supplying to that program the number of points we would like, and the upper limit, lower limit, and a pointer to the function which would give the right hand side and the x and y. So and then this function, this program is going to call in this. So first it determines what the x values to use. So that x values is used as lower limit plus I times xp. Xp is the interval, that is the h of our equations. This is the interval between 2 points, and I just divided that, determine this interval by equally dividing the whole interval upper limit to lower limit by n points. This is not required. We could have unequal intervals, but we in this case it's a simple division of equal intervals. And then I have that's my x value. Okay, and then I start with my boundary condition, which is y of 0 equal to 1. Okay, so I am going to solve this with the boundary condition y of 0 equal to 1. And then I would first call that function. Okay, now the derivs is my function here. Okay, so derivs is a function which gives me the derivative or the right hand side. Okay, so remember this program, I passed to this program a pointer to my function here, which I call my function. Okay, and this program receives it as derivs here. Okay, it receives it as derivs. Okay, so that when I supply here a pointer to the function which is the right hand side of my differential equation as my function, okay, and this function here that is the Runge-Kutta program is actually receiving it as derivs. Okay, so this is and then it calls the derivs with the x value and the y value at which I want to evaluate the derivatives, and this function would return the dy dx, the derivative at that point x and y. So both xx and yy are pointers, and dy dx1 is also a pointer. So I have allocated memory for all of that here. Okay, dy dx xy, dy dx, etc. So I put in some values into xx and yy, that is xi and yi at the starting point I equal to 0, let us say at I equal to 0. I put in the values to xx and yy, and it calls the derivs, and the derivs would return that value, the value at the derivative at that point xx and yy. Okay, so I do the first step here, that is, this is to calculate the k1. Okay, the k1 is now, I call it yn here, so which is y1 plus x times dy dx1. Okay, so that is just to evaluate the first point. Okay, so now I need to see, remember, I need to compute this quantity, right? So if to compute k2, I need to first know this point. Okay, so that is yn plus beta k1. So k1 is this, right? So h times f x and yn, and so I need to compute this quantity. So first I make a call to the derivative program, okay, which would return to me this function, and this function here, okay, and then I would multiply that by h and then add to this one, beta is 1, remember, so that I get this, and then I make a call again to that program with this y value, okay, and then this x value, okay, and then that will return to me k2, and then I substitute both back here and I get the yn plus 1. So that is what I am doing here. So I first took the x and y value, that is x0 and y0 I equal to 0, okay, and then I evaluated the derivative there, and then I computed this yn, that is y0 plus h times derivative, and then went to the next point in x, that is x1 now, I equal to 0 is x1, and then I use y now as this value, and then evaluate the derivative again, and now compute my y next as the yi plus the derivative times, the interval times the two derivatives, one at x and yn and other one multiplied by h, the h is outside here. So one is derivative x and yn evaluated at x and yn, and this is evaluated at xn plus h, that is xi plus 1 times yn and yn times h into the derivative at x and yn. So that, and I divide that by 2. Okay, that is the function value. Okay, so now this program will then this loop continues for all the I going from 0 to n minus 1, that is n points will be evaluated, and that would return that to the main program. So now what's my function here? So when this calls this derivs remember is mapped onto my function. So that's my function is this, it's simply saying minus 2y. So the equation I am solving here is simply y primed equal to minus 2y, okay, like we had done before, and with a boundary condition that y of 0 equal to 1. Okay, that's what we are trying to solve. Okay. So we solve this equation, okay, using this simple scheme here. Okay, that's what this program is, and then we can just see how it would run. Okay, so now that's between the upper limit 2 and lower limit 0, and the number of points we would use, we'll just use 5 points to evaluate that. Okay, and then we can plot this, so we can plot this function. So I have created a file there called Runge2.solution.dat, and we know the solution to the equation is exponential of minus 2 star x. That's the actual solution to the equation. Okay, so we can compare these two using. Okay, that's the solution. Just plot that. Okay, so now here is the function. Okay, and I will just change the points, which okay. So now this red spots are the one which we got as solution of the second order Runge-Kutta with just 4 points. Okay, with 5 points. We have 1, 2, 3, 4, 5, 6 points which we evaluated that at. Okay, and that's this green line is the actual solution to the equation 2, 5. So we can see that the second order Runge-Kutta is not all that accurate for 5-point integrations. If you want to get more accuracy, then we have to go to a higher number of points, which is not surprising because this method is just a predictor corrector method with just one loop. Okay, and so accuracy is not expected to be extremely high. So the one way to improve the accuracy is to go into larger number of points here. Okay, we have more number of points, or go to a higher order Runge-Kutta scheme. So when you go to a higher order Runge-Kutta scheme, we would use, instead of just using a function like approach like yn equal ak1 plus bk2, we would now use more derivatives. That is, we will now evaluate derivatives at more number of points. Now here we are evaluating derivative only at 2 points. Instead, in a higher order scheme, we would evaluate the derivative at higher number of points. Okay, that's the higher order Runge-Kutta scheme. We can see that here. For example, in the fourth order Runge-Kutta scheme, we would write yn as k1 plus 2k2 plus 2k3 plus k4. So again, so we will write that now we see we have to evaluate these are all derivatives on the right hand side of the function of the differential equation. So you evaluate now this at 4 points, hence it's called the fourth order Runge-Kutta scheme. So in this fourth order Runge-Kutta scheme, we are going to write yn plus 1 as yn plus 1 by 6 times. So times k1 plus 2k2 plus 2k3 plus k4. So these numbers, that is 6 and 1 here, 2, 2, 1. This is evaluated. This is also arrived at using a similar scheme as what we had done for the second order scheme. That is, we would write yn as yn plus 1 as yn plus, I would say ak1 plus bk2 plus ck3 plus dk4. Okay. And then we would write k1 as the function value itself there, and then k2 as a function value evaluated at x plus alpha h plus y plus beta k1. Okay. And then the k3 would be then function value evaluated x plus alpha some alpha 1 h plus beta 2 k2, etc. And then we would have to determine all those coefficients by a Taylor expansion. But now we will again we have to go to order higher than h cube, okay, to get this answers. So that is rather cumbersome, but it can be obtained. And then we would get this coefficient. One solution to that would be of this form, that is, all the coefficients here are 1 over 6. So there will be 1 here, 2 and 2 and 1. Okay, so that's what the fourth order scheme is. I'm not going to do all the derivation here, but that's a scheme. The scheme would be same as what we did for the second order Runge-Kutta scheme. So now this is what it is. Now k1 here is f at xn comma yn, okay, and k2 would be f at xn plus h by 2 comma yn, etc. Okay, so that's what we have to write. Okay, so then the scheme is the full scheme is the following. So yn plus k1 by 2. So this is yn plus k1 by 2, and k3 we would need this. So we just write this on the board here. So that is okay, h times f at xn plus h by 2 comma yn plus now k2 by 2. Okay, so and then k4 would be h at f xn plus h comma yn plus k3. Okay, so that's the solution, full solution. So we have to write yn plus 1 as yn plus 4 derivatives. So we have to evaluate the derivative at 4 times, okay, and then the order. So to determine this coefficient sitting here, so I said we would have to Taylor expand all the way to h4. So accuracy we are going to get is that much here, okay, and then we have k1 as h times the function value, okay, and k2 as h times the function value evaluated at now at xn plus hn by 2, so halfway in the interval. I have yn plus k1 by 2, and k3 is now hn, a function evaluated at xn plus hn by 2 again, but now yn plus k2 by 2, okay, using this derivative, and then k4 is now function value at h xn plus h, and then yn now is obtained using this derivative as a yn plus k3. Okay, so that's a 4 values k1, k2, k3, k4. Okay, so then we use that k1, k2, k3, k4, and then write the fourth order Runge-Kutta as yn plus 1 by 2 k1 plus 2 k2 plus 2 k3 plus k4. Okay, so we can see this also implemented in this simple code. So the code is very similar to what we just used, not different. Okay, so it's again the same way. So we have the first part of the code is anyway not different, so everything is the same. We just call here now, instead of calling earlier we were calling Runge 2 and now we are calling Runge 4, okay, and we again pass the number of points we require, the upper limit, lower limit, and the pointer to the function which supplies the right hand side of the differential equation, and we use the same right hand side of the differential equation that we will try to solve dy by dx is equal to minus 2y with the boundary condition y of 0 equal to 1. Okay, and then we would get so now this program in this Runge 4 program, right, which receives all of that, okay, we'll have to evaluate now the function values at 4 points. So that's what's done here. It uses the derivs, that is the my function, which would supply to me, given the x and y, what the derivative or the right hand side at that point is. Okay, now that is this function. So here, so I supply an x to start with the first part, determining the k1. Okay, I supply x and y, and I got the k1 here. So that this is my k1, right? Then I say that y. Now I do that in 4 different steps. So the y first I do. So the way I do this program is to write each step as, so first I compute this, and I say that my yn plus 1 is this. So I do first this sum, okay, and then to this sum I add 2k2 by 6, that is k2 by 3, and then to that term I add k3 by 3, and then I add k4 by 6. Okay, that's the way we're going to do in this program. That is, I'm going to start with saying that yn plus 1 is equal to yn plus k1 by 6, okay, and then I would say yn plus 1 is yn plus 1 plus k2 by 3, and yn plus 1 equal to yn plus 1 plus k3 by 3, and yn plus 1 is yn plus 1 plus k4 by 6. So that's just doing this in a serial order. Okay, so first I initialize yn plus 1 to this, and then I keep adding to that term k2 by 3, k3 by 3, k4 by 6. That's what this program is doing. Okay, it's just starting from that. Okay, it says yn plus 1 is yn plus h times derivative, that is function value divided by 6. Okay, and then it will shift now the x to x plus h by 2, and y to y plus the h times the derivative, that is k1 by 2. And again it will call the same program, that is, it will now supply to it the new x value, y value, it supply the new derivative, and then to the old the yn plus 1, now I am adding that divided by 3, that is h times this derivative evaluated with new x and y value, okay, add divided by 3, and I do that step once again with again shifting the x to that, and y, x is again taken as the same, xi plus xp by 2, y is now y of I plus xp times now this derivative evaluated here divided by 2, okay, and then I supply that, and then I get a new derivative, and then I add that to yn plus 1. So I do that 4 times, okay, till the last point where xx now xi plus h, that is xi plus 1, and y is now yi plus this derivative evaluated here, okay, and then I compute the new derivative at that point and add that to the function here. Okay, so that is this Runge 4. Okay, so we can run the Runge 4 here. Okay, so we could again supply 5 points to that. Okay, and we can now plot that along with this function with Runge 2. Okay, we'll also plot Runge 4 solution. Okay, so we compare that by plotting the solution which we got using a 5-point second order Runge-Kutta and a 5-point fourth order Runge-Kutta, and that's what we do here, and this is the plot which we obtained. So now green line is the actual solution, that is exponential minus 2x to a differential equation that y prime is equal to minus 2y. Yes, that's with boundary condition y of 0 equal to 1, and the red squares here are the one which we obtain with fourth order Runge-Kutta 5 points we use, and we got fourth order Runge-Kutta here, and now this blue circles are the ones which we obtain with fourth order Runge-Kutta using again 5 points. Okay, so you can see that the difference in the accuracy is quite remarkable, that we get by going to fourth order Runge-Kutta we get much more accurate values. So now so that's, we see that increasing the order of the Runge-Kutta scheme would definitely increase the accuracy. So another way to increase the accuracy would be to use a lower order scheme, but then evaluate the function value at use more points. Okay. In some sense both require larger number of evaluations of the function. So that is, now when you do a fourth order Runge-Kutta we are actually evaluating the function value at 4 different points. Okay, while a second order Runge-Kutta we are only evaluating the function at 2 points in this interval between xn and xn plus 1. So that's one. Okay, so we see this is one way of doing this, increasing the accuracy. But then again there is this question of what should be the interval between these 2 points should be. Okay, should I use the same interval for all the points, which is what I have done here. Between, if I look at any interval between xn and xn plus 1, they are the same. So the question is, should we always use the same interval? One would think that since we are trying to solve an equation of this form, that is the y prime is f of xy, so wherever the derivative is large, okay, we should go to smaller steps, right? So that's, see, finally we are writing the solution as something like this, right? So then we are saying that we are using the derivative, and to evaluate the function value at the next point we use the function value at that point plus the derivative multiplied by some interval. That's basically the scheme. All of this, the derivative multiplied by that interval. So you would think that if the derivative is large, then we should use a smaller interval, okay, so that we get a higher accuracy, because otherwise you could have large errors. Okay, so we should be able to write a program such a way that the step size, that is the h function, is not a constant, but instead it changes with depending on the function value itself. Okay, so that's what we call an adaptive step size. So we look at the function value, that is the right hand side of the equation, okay, and see how big it is, and then depending upon that we could choose the step size. Okay, that's one way of doing it. Another way of doing it is to just say that I will choose a step size and see what I would get, okay, and I would change the step size, and again I will go to the same point at xn value and then see and compare these two results. So that is another way of choosing the step size. Okay, so we will choose a step size such that we get a higher accuracy, and where the function value is not changing too fast, okay, we could use a larger step size, and where the function value is changing very fast, we should use a smaller step size. That is, looking at this graph, we would say that we should be using a smaller step size where in this region where the function value is decreasing rather fast, while we could use a larger step size here where it is not decreasing so fast. Okay, that's the basic idea behind what's called the adaptive step size algorithms. So we look at that now. So in an adaptive step size Runge-Kutta, we would get the yn plus 1 from using two different step size, so that we could use the step size h first, okay, and then we could half the step size and again go to that same x value, and that is in 2 steps now. And then we would now say that I would evaluate y at x plus h, okay, by using y at x plus let's say some h times. Now let me use any of those schemes. Okay, so let's say Runge-Kutta 4, second order Runge-Kutta. So then I would write this as f at so I'll say k1 plus k2 by 2, right? So I would just use k1 plus k2 by 2, where now to determine k2 I would use h times f function value evaluated xn plus h, right, and yn plus k1. Okay. So now this is h I use, and I get x plus h from this scheme, let's say. Okay. So that's maybe the first step, and the second step what I do is I take h to h by 2. Okay. And then I would evaluate that in the second step. Okay, I would use half the step size, and then I would say I will evaluate x plus h by 2 first, okay, from y at x plus now k1 and k2 evaluated at x1 plus h by 2. Okay, that is function value h times the function value at xn yn h by 2 times. Now we are going by step size half. Okay, so h is going to h by 2, so we are doing a h by 2 steps, and then again the function value evaluated at xn plus h by 2 and yn plus k1. Okay, so that is what I would do, and there is a half there outside again. So okay, so that will be my second step. Okay. Now I do this once again, then I go to y at x plus h, from y at now x plus h by 2, right, and then do the same thing again, that is half times now h by 2, now the function value at xn plus h by 2 yn plus half, right, yn plus half I would call it. Okay, so yn plus half is yn at y at xn plus h by 2. Okay. So then plus h by 2 times f at xn plus h now comma yn plus k1. Okay. So I do this in 2 steps. I did it in 1 step here, and I do it in 2 steps. Okay. So let me call this value as yo and this value as y1. And then I compute an error which would be y1 minus yo divided by y1 mod of that. Okay, and then if this method is if my values are correct, and then whether I should go by step h or step h by 2, I should get the same answer. That should be, this should be 0 or should be very, very small. So if it is not small, then I will go back to this loop again and halve the step again. Okay, so I will go to half the step again, and then I will continue this loop till I get the same value. Okay, so that is the idea behind adaptive step size. So what is the summary? The summary is that I go to x plus h, okay, here in 1 step, okay, or I go to x plus h by 2 steps, x plus h by 2 and then to x plus h. For using x here and x plus h by 2 here, I go it in 2 steps. Okay, and I compare the values I get from these two and compute an error. Okay. Now if this error is significant, okay, compared to depending upon what accuracy you want, if this error is significant, okay, then I will go back here and again halve the step. Okay, now I say my y0 is now this y1, and I will compute in y1 again by halving the step and again going in 2 steps. Okay. So I will keep doing this, okay, till I get the same values from this y1 and y0. Okay. And that's the step size, and thus determine the step size which I want to use. Okay. And then I go to the next point of the integration using that step size, okay, and as my initial step size prediction. Okay. and then I will again check this value, and if these two values are same, okay, that if in the first step itself I use these two values are same, then I can actually increase my step size. Okay, so I can go from h to 2h, etc. So I keep doing this way. Okay, so that's what we will see in this particular program. So as I said that I will go in steps, I choose an interval h, go compute the value yn plus 1, okay, and that's which I call y1, okay, from yn by a single step, and half the step value of h, okay, and compute which I call now we call y2 here, again yn plus 1, and I compare these two and define error here y2 minus y1 by y1, okay, and then I'll compare this with some predetermined error tolerance which I have put in, okay, and we can use this equation to solve the differential equation which we just looked at. So that is given here in this program. So I am using a fourth order Runge-Kutta using adaptive step size here. Okay, now this program is slightly longer because we have to determine the step size. So I written it slightly differently. Okay, so now this function is going to call Runge-Kutta order 4, but now with adaptive step size. Okay, that's what we are going to call. Okay, now I call that as Runge-Kutta 4. Okay, now this is with adaptive step size. Okay, now to that now in this part we are only doing this. Now I can't divide my interval now to some predetermined number of points. Okay, so instead of that I will ask the program now asks for a step size, initial guess to the step size. You give some step size, okay, and then the program will determine automatically, it will determine by using this procedure which I just described, what is the actual step size, optimum step size to be used. So the only thing which we supply, so we have to determine the step size from the program, so we can't divide that into some number of intervals initially. So what we do is we'll just go step by step. We'll say we start from x0 in this program, okay, and then we call this Runge-Kutta order 4, which will return to me the y value at the next point, and what will be the next point is, and that will be determined by what step size it will use, right? So that is what it will return. Okay, so we just start with give some x0, okay, as the lower limit, okay, and the y value, this is a boundary condition, y0 is 1, so this is a boundary condition. I start with this boundary condition and I call this program, okay, which will return to me the x and y value and the step size it used to determine the x and y value at the next point. Okay, so that's what, and then I use that as my next initial value, right? So I use this initial value to get my next point, and I use that as the initial value and call this program again until I do this till it will reach the upper limit. Okay, so that's what. Now we have to go step by step. Okay, so we use the initial values x0 and y0, and go to the next step using this program, okay, and which will return to me the step size used, okay, and I use that and then go to the next, and now I use the x1 y1 which it returned. Okay, it will return the x1 y1, that is the next point and the y value there. I use that point and go to the next one and determine the x and y and the next point, etc. Okay, so now how does this program determine this step size? That's a method which I just described. Okay, so it starts with the step size which you supplied. Okay, so this program we call that with the step size which we kind of predicted or we guessed. Okay, and then we supply the pointer to the function and the x y value. These are the things it will return. Okay, so it will come here. Okay, and then it would use the x1 y1 as the value which we just supply, the initial values. Okay, and then I have a tolerance which also we have to set in, and the tolerance is now I set it here as 10 power of minus 2. Okay, that's 110 power of minus 2 is my tolerance. Okay, and then it would determine the first step, that is xn plus h, and it will do this fourth order Runge-Kutta. So this point up to starting from here, so we supplied the initial value, and it is going to do x1 as x1 plus h. X1 is the initial value, y1 is the initial value again. Okay, so it is going to take that x and y, okay, and then compute the derivative, and that is our k1, and then it increases the step size by h by 2 using the step size which we guessed as an appropriate step size. okay, and it will compute k2, and then it will compute k3, and then it will compute k4, right, and I will add all of them into y. So that's our y1 at the end. So this is the same as the fourth order Runge-Kutta which we just looked at. So once we have the with that y value, okay, so now then we go here. If the first loop that is it equal to 0, that's the first loop, it will increase, it will store that y value as yn, okay, and it will halve the step size, okay, and it resets its x and y value to the initial value which we just used. Okay. So we'll reset the initial value to this and halve the step size. It goes back here again, okay, and computes this whole thing again. Okay, it will compute the whole thing. Now it will compute it twice, okay, because it is equal to 1, and then what it does is, so this is when it equal to 0. When it equal to 1, it will now store the intermediate value in y1 and x1, okay, and starts again. So now it used h by 2 starting from x0 y0 and went to x1 y1. It compute that once again. Okay, now it goes to h. Okay, x1 goes to h, and y1 is now the initial value at here, and it goes back there and again computes that quantity. Remember, this h is h by 2 because I put h equal to h by 2 here. Okay, so now that's my initial value, and it does one more loop. Okay, so in these two loops it completes that h, and it comes out here. Okay, and now it has two y values. Okay, it has a yn and a new y1. Okay, now it computes that error yn minus y1 by y1. Okay, now the error tolerance is if the error is below tolerance, and then it will say that the h next is to be used is 2 times the h value. Okay, or if it's greater than the tolerance, it will reset the yn value and the x1 and y1 value as x0 y0 and halve the step size further. Okay, yes, halve the step size here again and go back and do that again once more. So it continues this process, okay, and comes out with a h next. Okay, so now we'll do the same thing here. So now we'll do this for the same function, that is minus 2y. Okay, d1 equal to minus 2y, and we will run this and see what we get. Okay, so we'll run this program here, and we can compare this with our results. Okay, so we'll just use the now Runge for adaptive.c. We'll compare that. So we want initial step size. We are going from 0 to 2. We'll use the step size as 1. Okay, and it has done something, and now we'll just plot that here. So here is the plot of that thing. The blue points here are from the adaptive step size. As you can see that the interval is not the same all throughout. So you have a larger interval here and a smaller interval there. So and the red points which you obtain here are the one from the Runge-Kutta 4 using 5-point integration. So here we see that again we have got a very high accuracy, but we just started with step size 1, but it has chosen a step size which is quite different from what we use as 1, because the whole interval is 2. So we suggested that we use step size 1, and which is obviously not satisfactory. So it has gone back and chosen a step size which fits into the accuracy which we wanted, that's 10 to the power of minus 2. So now that's the different methods which we have to use for solving a first order Runge-Kutta first order differential equation. So we are now seeing that we can use an Euler scheme, or use a predictor corrector scheme, or use 2 different orders of Runge-Kutta scheme. So now that's all for the first order equation. So what if you have to do a higher order differential equation, let's say second order or third order differential equation, and then what we'll have to do is to split that equation into many first order equations and then use the schemes. That's what we would use, the same Runge-Kutta or predictor corrector kind of schemes. And that's what you would see in the next class.